Okay, benzene and aromaticity. Why this chapter? The reactivity of substituted aromatic compounds, more than that of any other class of substances, is intimately tied to their exact structure. As a result, aromatic compounds provide an extraordinarily sensitive probe for studying the relationship between structure and reactivity. We'll examine this relationship here and in the following chapter, and we'll find that the lessons learned are applicable to all other organic compounds, including important substances such as the nucleic acids that control our genetic makeup. Boom. In the early days of organic chemistry, the word aromatic used to describe such fragrant substances as benzaldehyde, which really does smell amazing, and toluene and benzene. We soon realized, however, that substances grouped as aromatic differed from most other organic compounds in their chemical behavior. Today, the association of aromaticity with fragrance has long been lost, and we now use the word aromatic to refer to the class of compounds that contain six-membered rings with three alternating double bonds. Many naturally occurring compounds are aromatic in part, including steroids such as esterone, and well-known pharmaceuticals such as the cholesterol-lowering drug atorvastatin, marketed as Lipitor. Benzene itself causes a depressed white blood cell count on prolonged exposure and should not be used as a solvent. Simple aromatic. Okay, so here we go. Naming aromatic compounds. Simple aromatic hydrocarbons come from two main sources: coal and petroleum. Coal is an enormously complex mixture consisting primarily of large arrays of benzene-like rings joined together. Thermal breakdown of coal occurs when heated to 1,000 degrees in the absence of air, and a mixture of volatile products called coal tar boils off. Fractional distillation of coal tar yields benzene, toluene, xylene, naphthalene, and a bunch of other aromatic compounds. All right, so here we can get a look at some aromatic compounds. Benzene, toluene, xylene. This is an interesting thing, by the way, and I think it just means it's ambiguous as to where on the ring it is. It's kind of a niche thing in my mind, but indene. So indene is important because of indole and my favorite, tryptophan. Naphthalene, I worked in the lab. Biphenyl, anthracene, and phenanthrene. It's pretty amazing, actually. These are pretty cool. It's totally planar. Unlike coal, petroleum contains few aromatic compounds and consists largely of alkanes. During petroleum refining, however, aromatic molecules are formed when alkanes are passed over a catalyst at 500 C in high pressure. Aromatic substances, more than any other class of organic compounds, have acquired a large number of non-systematic names. It's discouraged, but for example, toluene is methylbenzene, hydroxybenzene is phenol, and aminobenzene is aniline, and the list goes on. So here we go, toluene. So these are common names of some aromatic compounds. Phenol, aniline, acetophenone. I always forget this one, acetophenone. Benzaldehyde, benzoic acid, orthoxylene, styrene. Styrene's pretty cool. You can do a lot with styrene, actually. Styrene's cool because you have a alkene here, and you could do a ton of alkene stuff here. You know, I could put bromine here and make it a terminal aryl halide. Is that what it's called? An aryl halide? Monosubstituted benzenes are named. Actually, it's monosubstituted benzenes are named systematically in the same manner as other hydrocarbons. with dash benzene as the parent name. Thus, bromobenzene, nitrobenzene, propylbenzene. Alkyl substituted benzenes are sometimes referred to as arenes and are named in different ways depending on the size of the alkyl group. If the alkyl substituent is smaller than the ring, the arene is referred in carbon count. The arene is referred to as an alkyl substituted benzene. If the alkyl substituent is larger than the ring in carbon count, the compound is referred to as phenyl substituted alkane. The name phenyl pronounced phenyl, abbreviated as pH, is used for the -C6H5 unit when the benzene ring is considered a substituent. The word is derived from. It's actually cool that Michael Faraday found it. Dude, he's goated for sure. The name benzyl is used for basically a phenyl methyl group. Disubstituted benzenes are named using the prefixes ortho, meta, and para. An ortho disubstituted benzene has its two substituents in a 1,2, meta is a 1,3, and para is a 1,4. So here, let's look at these names. Ortho dichlorobenzene, meta dimethylbenzene, parachlorobenzaldehyde. Now that's interesting. Okay. The ortho, meta, and para system of nomenclature is also useful when discussing reactions. For example, we might describe the reaction of bromine with toluene by saying reaction occurs at the para position, meaning that the position para to the methyl group that's fine. As with cycloalkanes, benzenes with more than two substituents are named by choosing a point of attachment as carbon 1 and numbering the substituents on the ring so that the second substituent has as low a number as possible. If ambiguity still exists, number so that the third or fourth substituent has as low a number as possible until a point of difference is found. The substituents are listed alphabetically when writing the name. All right, let's try to look at these and figure out what's going on here. So we're given at least carbon 1. So I would say 4-bromo, 1,2-dimethylbenzene. Nice. Now here, are you supposed to just say 2,5-dimethylphenol? Boom. Now here, one methyl, 2,4,6-trinitrobenzene. But nitro comes before benzene, so is it 2,4,6? No, it should be one methyl. Oh, actually, that's interesting. I would say 1-methyl 2,4,6-trinitrobenzene. Oh, interesting. No way, TNT. Okay. Note in the second and third examples that phenol and toluene are used as the parent names rather than benzene. Any of the monosubstituted aromatic compounds shown in table 15.1 can serve as a parent name, with the principal substituent. So I should have known. Where OH is and CH3 is the C1. Does it have to be? I guess it has to be. You wouldn't write 2-toluene. Okay. Meta, para, ortho. Oh, that's interesting. All right, let's get into it. So this should be I mean, I don't know how you make it with the ortho or with the meta name. So I would just do one bromo, three chloro, benzene. Two, three, four. One, two, three, four, five. So this is less than phenyl. So that means phenyl is the main ring. Right, so then now we're just going to name this. So this is going to be, but does this have to be carbon 1? If that is, it would be 3-methylbutane. But then do you just write 3-methylbutane benzene? 3-methylbutyl. 3-methylbutyl benzene? I'll have to check on that one. That one's interesting. Here we go. This one. Oh, I got this one. Yo, I'm good on this. This is gonna be para bromo aniline. But a name that I would probably prefer. Honestly, I prefer this more. 4 bromo. Um, amino one amine. Oh, benzene. Or alternatively, we could just do 4 bromo, 1 amino. Oh wait, that's what I already wrote. You probably can drop the 1. Uh, I would say 1,4-dichloro. Oh, 2-methylbenzene. Dude, I wish I had time to just study for this. Like, way better. It's just fun. Like, I actually like this stuff. Just rules, you know? I love rules. All right, what is this one? E. 2-ethyl. Oh, wait, no, wait. Oh, shoot. Oh, wait, no, it's probably this. It's probably 2,4-dinitro ethyl benzene. 2,4-dinitro ethyl benzene. You sound so smart reading chemistry. Like, it's actually pretty basic, but you sound so damn smart. Like, today I was just like, the synthesis of vitamin D occurs by a photochemical electrocyclic or pericyclic reaction. And you just sound so cool. All right. What is F testing? Should it just be 1, 2, 3, 5? Tetramethylbenzene? Alternatively, I could see it being 2, 3, 5 trimethyl toluene. Okay, wait. A. Oh, you can do that? Meta. So this is the correct answer. Meta, bromo, chloro, benzene. I didn't know you could just do that. That's pretty cool. All right, 3-methylbutylbenzene. So I definitely got that one right. That's good. C, parabromoaniline. This is the right one. I figured that was going to be the right one. D. But now, for instance, if I did 4 bromo, 1 amino, benzene, is it going to know what the hell I'm talking about? Oh my gosh, this is why AI is so sick. Because, like, I just say, what is this? Is the IUPAC style name for parabromoaniline? No, wait. Um, is there a UTF-8 benzene? Oh wait, I think I'm just supposed to do it like this. Hexagon LR bonds. Benzene Unicode. That's pretty cool, dude. I didn't know that we get a benzene ring as a Unicode. That's fun. Okay. Enough horsing around. D25 dichlorotoluene. What did I write? Oh yeah, I did that one wrong. Okay. I mean, at some point, this is like too much, you know. E1. Oh, I did 2,4-dinitroethylbenzene, but I guess what you have to do is 1-ethyl 2,4-dinitro benz. This is the book answer. Dude, what? Okay, so this was right. Why was the tetramethyl right? I don't get it. Whatever. All right, parabromochlorobenzene. It's literally this, but the chloro is over here. Parabromotoluene. It's literally this, but this is a methyl. Metachloroaniline. It's this, except this is here and it's a chlorine. 1-chloro-3,5-dimethylbenzene. This is the only one I may draw. All right, get our benzene. 1-chloro-3,5-dimethyl. Okay, that one's easy. All right, let's get into some actual chemistry. All right. 15.2, structure and stability of benzene. Oh, I got the chat up, just in case. Has 6 fewer hydrogens than the 6-carbon cycloalkane cyclohexane, and is clearly unsaturated, usually being represented as a 6-membered ring with alternating double and single bonds. Yet it has been known since the mid 1800s that benzene is much less reactive than typical alkenes and fails to undergo typical alkene addition reactions. Cyclohexene, for instance, reacts rapidly with bromine gas and yields the addition of the 1,2-dibromocyclohexane. But benzene reacts slowly with bromine gas and gives the substitution product bromobenzene. Really? We can get a quantitative idea of benzene stability by measuring heats of hydrogenation. Cyclohexene, an isolated alkene, has a heat of hydrogenation of minus 118 kilojoules per mole. And 1,3-cyclohexadiene, a conjugated diene, has a much higher or lower heat of hydrogen. Oh, this value's a bit less because conjugated dienes are more stable than isolated dienes because of resonance. Carrying the process one step further, we might expect the heat of hydrogenation for a cyclohexatriene to be a bit less than 3 times the single alkene, or 3 times the cyclohexene value. The actual value is minus 208 kilojoules per mole, some 148 kilojoules per mole less than expected. Because of this difference in actual and expected energy released during hydrogenation, benzene must have 148 kilojoule per mole less energy to begin with. In other words, benzene is more stable than expected by a lot. By like a lot. It's actually more stable than the diene. Further evidence for the unusual nature of benzene is that all its carbon-carbon bonds have the same length, 139 picometers, which is intermediate between a single and double bond. In addition, the electrostatic potential map shows the electron density is all identical, so it's super symmetric. Thus, benzene is a planar molecule with the shape of a regular hexagon. All CCC bonds are 120 degrees, all 6 carbon atoms are sp2 hybridized, and each carbon has a p orbital perpendicular to the plane of the 6-membered ring. Because all 6 carbon atoms and all 6 p orbitals in benzene are equivalent, it's impossible to define 3 localized pi bonds in which a given p orbital overlaps only one neighboring p orbital. Rather, each p orbital overlaps equally well with both neighboring p orbitals, leading to a picture of benzene in which all 6 pi electrons are free to move about the entire ring. In resonance terms, benzene is a hybrid of 2 equivalent forms. Neither form is correct by itself. The true structure of benzene is somewhere in between the 2 resonance forms, but it's impossible to draw with our usual conventions. Because of this resonance, benzene is more stable and less reactive than a typical alkene. Chemists sometimes represent the 2 benzene resonance forms by using a circle to indicate the equivalence of the this representation has to be used carefully because it doesn't indicate the number of pi electrons in the ring. Having just seen a resonance description of benzene, let's now look at the alternative molecular orbital description. We can construct wow, this is cool. I actually like molecular orbital theory now. It's like pretty interesting. Ever since the thing about the standing wave, I've thought that it's cool. We can construct pi molecular orbitals for benzene, just as we did for the butadiene. If 6p atomic orbitals combine in a cyclic matter, 6 benzene molecular orbitals result. The 3 low-energy molecular orbitals, psi 1, 2, and 3, are bonding combinations, and the 3 high-energy orbitals are anti-bonding. So what is up with this not being drawn? Oh, because these are nodes. Those must be nodes of the wave. Similarly, these are nodes. Those are like true zeros. Interesting. Yo, mama. All right. The bonding orbitals psi 2 and psi 3 have the same energy and are said to be degenerate, as are the antibonding psi 4 and psi 5. The orbitals psi 3 and psi 4 have no pi electron density on 2 carbons because of a node passing through these atoms. Yeah. Note that the 2 bonding orbitals psi 2 and psi 3 have the same energy as do the two. Such orbitals with the same energy are said to be degenerate. Note that the 2 orbitals psi 3 and psi 4 have nodes. Did they just repeated it? What the heck? Leaving no pi electron density on these carbons. That's actually pretty interesting. The 6p electrons of benzene occupy the 3 bonding molecular orbitals and are delocalized over the entire conjugated system. Pyridine is a flat hexagonal molecule with bond angles of 120. It undergoes substitution rather than addition and generally behaves like benzene. Draw a picture of the pi orbitals of pyridine and explain its properties. Check your answer by looking ahead to section 15.5. Oh yeah, okay, so the lone pair is out on this one. That's the only difference. So it's basically benzene with an sp2 lone pair. All right, we're breezing through it. 15.3 aromaticity and the how do you say this? How do you say this? Dude, I want to learn the phonetic alphabet, man. I low-key feel like this might be faster. Oh wait, actually, hold on. What's faster? Hucal. Hucal. E. Hecal. Hucal. All right, Hucal. That's what I'm gonna say. And the Hucal 4n plus 2 rule. Let's list what we've said so far about benzene, and by extension, other benzene-like aromatic molecules. Benzene is cyclic and conjugated. Benzene is unusually stable, having a heat of hydrogenation about 150 kilojoules per mole less negative than we might expect for a conjugated cyclic triene. Benzene is planar and has the shape of a regular hexagon. All bond angles are 120 degrees. Okay. All right, this is a good comment. Benzene undergoes substitution reactions that retain the cyclic conjugation rather than electrophilic addition reactions that would destroy it. Benzene can be described as a resonance hybrid whose structure is intermediate between two line bond structures. This list might seem to be a good description of benzene and other aromatic molecules, but it isn't enough. Something else called the Huckel 4n plus 2 rule is needed to complete a description of aromaticity. According to a theory devised in 1931, a molecule is aromatic only if it has a planar monocyclic system of conjugation and contains a total of 4n plus 2 electrons, where n is an integer. Let's read it again because it's pretty important. A molecule is aromatic only if it has a planar monocyclic system of conjugation and contains a total of 4n plus 2 pi electrons, where n is an integer. In other words, only molecules with 2, 6, 10, 14, 18 pi electrons can be aromatic. Molecules with 4n pi electrons, like 4 and 8, can't be aromatic. Let's look at this. Let me draw a stop sign. Why not? Actually, it seems like you could. Even though they may be cyclic planar and apparently conjugated, in fact, planar conjugated molecules with 4n pi electrons are said to be anti-aromatic. Or yeah, actually, cyclobutadiene is an interesting, simpler example. Let's look at several examples to see how the Huckel rule works. Cyclobutadiene has 4 pi electrons and is anti-aromatic. As indicated by the electrostatic potential map, the pi electrons are localized in 2 double bonds rather than delocalized around the ring. Cyclobutadiene is highly reactive and shows none of the properties associated with aromaticity. In fact, it was not even prepared until 1965, when someone was able to make it at low temperature. Even at minus 78 C, however, cyclobutadiene is so reactive that it dimerizes by a Diels-Alder. Oh, that's a fucking crazy molecule, actually. What is that, dude? So, cyclobutadiene dimerizes. What do you call this, dude? This is a crazy looking molecule, actually. 3 4-membered rings all fused? I knew it was gonna have a crazy name, bro. Holy cow. Let's just write this down because that's insane. I knew it was gonna have a crazy name. Tricyclo bracket 4.2.0.0 superscript 2 comma 5 octa 37 diene. I mean, come on. If that doesn't make you like wonder about efficient ways to turn graphs into to turn a graph structure into a linear structure, then I don't know what to tell you because that's insane. I do want to learn about those bicyclic naming schemes, but not now. Okay. All right. Cyclooctate train has 8 pi electrons, but when it was first prepared in 1911, it was not found to be particularly stable. In fact, its pi electrons are localized into 4 double bonds rather than delocalized around the ring. And the molecule is tub-shaped rather than planar. It has no cyclic conjugation because neighboring p orbitals don't have the necessary parallel alignment for overlap, and it resembles an open-chain polyene in its reactivity. Huh. It's pretty interesting. X-ray studies show that the CC single bonds in cyclooctate train are 147 picometers long, but the double bonds are less. The proton NMR shows a single sharp resonance. So what's so special about 4n plus 2? Why does the 2, 6, 10, 14 lead to aromatic stability, while other numbers of electrons do not? The answer comes from molecular orbital theory. When the energy levels of molecular orbitals for cyclic conjugated molecules are calculated, it turns out that there is always a single lowest lying MO, above which the MOs come in degenerate pairs. Thus, when electrons fill the various molecular orbitals, it takes 2 electrons or 1 pair to fill the lowest lying orbital, and 4 electrons or 2 pairs to fill each of n succeeding energy levels. Any other number would leave an energy level partially filled. The 6... Oops. Oh, I hate this. It's like, why doesn't it just leave me alone when I... The 6 pi molecular orbitals of benzene were shown previously, and their relative energies are shown again. Lowest has 2, the next has 4, and they're degenerate. I feel like that wasn't a satisfying answer. They just said... All right. To be aromatic, a molecule must have 4n plus 2 pi electrons and must have a planar monocyclic system of conjugation. Cyclodecapentaene. Oh, okay. Oh, pentaene. So what did this say, though? Oh, I said this wrong. Cyclooctatetraene. Cyclooctatetraene. Yeah, that makes sense. Okay, so here we have cyclodecapentaene fulfills one of these criteria but not the other and has resisted all attempts at synthesis. Explain. Ooh. But this one is but this one I thought satisfies the rule. Isn't it 10? I gotta look at the answers. Okay, so yeah, so the 4n plus 2 is only the electron count test, not the whole aromaticity test. For aromaticity, you need all three of the things. Cyclic, fully... Okay, so wait, actually... We need cyclic, fully conjugated, planar, and 4n plus 2. So what besides benzene? What the hell is this? What is that? Whoa. Naphthalene's pretty interesting. Wow. That's cool. This isn't planar though. All right. So it's okay. So 15.5's answer was that hydrogen steric crowding prevents planarity. Breezing through next section, aromatic ions. Oh, here we go. Yeah, so we're getting to some of the other cases. Okay, according to the Hugel criteria for aromaticity, a molecule must be cyclic, conjugated, nearly planar with a p orbital on each atom, and have 4n plus 2 pi electrons. Nothing in this definition says that the number of pi electrons must be the same as the number of atoms in the ring. or that the substance must be neutral. In fact, the numbers can differ and the substance can be an ion. Thus, both the cyclopentadienyl anion and the cycloheptatrienol cation are aromatic even though both ions are even though both are ions and neither contains a six-membered ring. To understand why the cyclopentadienyl anion and the cycloheptatrienol cation are aromatic, imagine starting from the related neutral hydrocarbons (1,3) cyclopentadiene and removing one hydrogen If that carbon then rehybridizes from sp3 to sp2, the resultant products would be fully conjugated, with a p orbital on every carbon. There are three ways in which the hydrogen might be removed. The hydrogen can be removed with both electrons, leaving a carbocation product. The hydrogen can be removed with one electron, leaving a carbon radical. And finally, no electrons, leaving a carbanion. All the potential products formed by removing a hydrogen from 1,3-cyclopentadiene and from 1,3,5-cycloheptatriene can be drawn with numerous resonance structures, but Huckel's rule predicts that only the 6-pi electron cyclopentadienyl anion and the cycloheptatrienol cation can be aromatic. Both the carbocation and the carbanion are sp2, so that kind of makes sense. In practice, both the 4-pi electron cyclopentad In practice, both the 4-pi and the 5-pi electron cyclopentadienyl are highly reactive and difficult to prepare. Neither shows any sign of the stability expected for an aromatic system. However, the 6-pi is easily prepared and remarkably stable. In fact, the anion is so stable and easily formed that 1,3-cyclopentadiene is one of the most acidic hydrocarbons known. Whoa, that's actually wild. Wait, but it's not that acidic. I don't know what I'm talking about. It's still not that acidic. I mean, I guess it's interesting that it's one of the most acidic hydrocarbons known, but I mean, I guess that makes sense. Out of hydrocarbons, that's pretty cool though. I mean, that's actually pretty interesting, I would say. So if we look this up, then cyclopenyldiene. The thing is, if I look it up, what do we expect to get? Is it going to be a substance? Is it going to be a compound or is it a substance? It's all just in other stuff. So it's not really. But what if I go to. It's kind of weird. I'm always shocked by how little is in PubChem, honestly. In the same way, the 7 and 8 are. I'm not drawing those resonance structures. 5 resonance. Are you kidding? We can read the answer though. Cyclooctatetraene readily reacts with potassium metal to form the stable cyclooctatetraene dianion. C8H8 2 minus. I have no idea. Oh. I still don't really get why 4n plus 2 is so important. Look back once again. All right. 15.5. Aromatic heterocycles. Okay. Pyridine and pyrrole. Look back once again at the definition of aromaticity. Cyclic conjugated 4n plus 2 electrons. Nothing in this definition says that the atoms must be carbon. In fact, heterocyclic compounds can be aromatic. A heterocycle is a cyclic compound that contains atoms of more than one element in its ring, usually carbon, nitrogen, oxygen, sulfur. Pyridine, pyrimidine, for example, are six-membered heterocycles. Oh, I actually am starting to see why pyrrole, because it's got the lone pair, and it's sp2. Um, Actually, pyridine makes sense. Pyridine is much like benzene in its pi electron structure. Each of the 5 sp2 hybridized carbons has a p orbital perpendicular to the plane of the ring, and each p orbital contains 1 pi electron. The nitrogen atom also is sp2 hybridized and has 1 electron in a p orbital, bringing the total to 6. The nitrogen lone pair are in an sp2 orbital in the plane of the ring and are not part of the aromatic system. Pyrimidine is a benzene analog that has 2 nitrogen atoms in a six-membered unsaturated ring. Both nitrogens sp2 and each contributes 1 electron to the aromatic pi system. Pyrrole and imidazole are 5-membered heterocycles. Yet both have 6 pi electrons and are aromatic. In pyrrole, each of the 4 sp2 hybridized carbons contributes 1 pi electron. In pyrrole, each of the 4 sp2 hybridized carbons contributes 1 pi electron, and the sp2 hybridized nitrogen atom contributes the 2 from its lone pair, which occupies a p orbital. Imidazole is an analog of purol that has 2 nitrogen atoms in a 5-membered unsaturated ring. Both nitrogens are sp2 hybridized, but one is in a double bond and contributes only 1 electron to the aromatic pi system, and the other is not in a double bond and contributes 2. I feel like there's some fun combinatorics in figuring out, like, now that you can, like, you have like a bigger space to play around with the electron counts so that you get all the things that you want to satisfy, and you could probably make like you could probably generate like a pretty large class of synthesizable, like, for instance, nitrogen substituted ring structures. Like, already here, what if you try to go to bigger rings? Like, what if you went to the hept, the 7? It just seems like you could do a lot. Note that nitrogen atoms have different roles depending on the structure of the molecule. The nitrogen atoms in pyridine and pyrimidine are both in double bonds and contribute only 1 pi electron to the aromatic sextet, just as a carbon does in benzene. The nitrogen atom in purol, however, is not in a double bond and contributes 2 pi electrons, which are its lone pair to the aromatic sextet. In imidazole, both kinds of nitrogen are present, double bonded and the single bonded, or the sigma bonded. Pyrimidine imidazole rings are particularly important in biological chemistry. Pyrimidine, for instance, is the parent ring system in cytosine, thymine, and uracil, 3 of the 5 heterocyclic amine bases found in nucleic acid. I didn't realize how much nitrogen was in these rings. I forgot what they're called. Yeah, they're just called alkaline hydrothermal vents. This picture rules. Dude, I gotta reread. Now that I've taken OChem, I actually have to reread the Vital Question because that book is So good. Dude, that's the like that book makes you just want like think about where we come from, man. Obviously, but it's just so good. Yo, what's up, Ramesh? All right. So okay, so yeah, this is what I wanted to know. So cytosine. Wait, cytosine, thymine. My computer's kind of going off the charts. I'm gonna try to close some stuff. Not that it helps. Wait, actually, wait. I don't know, Loki, I need a better computer for streaming. Thiophene, a sulfur-containing heterocycle, undergoes typical aromatic substitution reactions rather than addition reactions. Why is... Oh, yeah. Thiophene. That's really interesting. Okay, so thiophene also has the same thing, except you kind of get both. You get the lone pair, and then you also get 2 pi electrons. Draw the orbital picture of furan. Oh yeah, because sulfur and oxygen are so similar. This is literally the exact same picture as this. You just replace O with or S with O. Thiamine or vitamin B1 contains a positively charged 5-membered ring, membered nitrogen sulfur heterocycle called the thiazolium ring. Explain why the thiazolium is aromatic. Dude, what? Two electrons here, 2 electrons here. It's not clear to me. I guess this thing contributes a P, and so then it's a let's look at the answer key. So here's furan. It's literally the exact same. Okay, and that's what I thought. The heterocyclic thiazolium ring contains 6 pi electrons. Each carbon contributes 1 electron. Nitrogen contributes 1. Each carbon contributes 1, nitrogen contributes 1, and sulfur contributes 2. So we get 6. Oh, we're not doing this anymore. Engineering's on Wednesday, so like presumably after the chem exam, I can like pull an all-nighter. What am I studying? Am I studying any other STEM field? What's STEM? What is that? I don't study plants, bro. Stems? I don't even know what that means. Okay. All right, so we understand. Oh, here's the picture. I was wondering. All right, here we go. I was excited about this one. 15.6. Polycyclic aromatic compound. The Huckel rule is strictly applicable only to monocyclic compounds. But the general concept of aromaticity can be extended to include polycyclic aromatic compounds. Naphthalene with two benzene-like rings fused together, anthracene with three, benzoapyrene with five, and coronine with six. Dude, coronine. Holy shit. Dude, look at this thing. I wonder how big we could go. Like, I wonder, can we make like a million ring plate? Can we just make a flat sheet of I'm looking at coronine, which is a totally planar series of fused hexagonal rings. And my question is, how big could we make a sheet of these fused rings? Like, what if we wanted to make like a really, really big one of these? Do we have any way to make it? Let's see. I'm sure, because I feel like a lot of material science. I mean, the thing is, they usually work with like weird metals and crystals. So I don't know about this, but like, imagine you could just like keep extending this thing out with more and more and more rings. My guess is you could build it pretty big. Nano. Oh, that's what graphene is. Yeah, that's what I was thinking. Okay, so that's what graphene is. But is it aromatic? Graphene occurs naturally. Well, I mean, yeah, okay. Coronine exists. Where does coronine come from? Actually, that's kind of what I want to know. All right, so that's what graphene is. That's pretty cool. I never actually knew that. Graphene. What did you say? Stem is not related to any tree? I don't know, man. Plants have stems. I don't know if you know that, but plants have stems. Oh, really? This is in tobacco smoke? Uh, All polycyclic aromatic hydrocarbons can be represented by a number of different resonance forms. Naphthalene and other polycyclic aromatic hydrocarbons show many of the chemical properties associated with aromaticity. Furthermore, naphthalene reacts slowly with electrophiles such as bromine gas, gives substitution products rather than double bond addition products. The aromaticity of naphthalene is explained by the orbital picture. Yeah, because each time you add a fused ring, you add 4. Huh. That is really interesting. That is really interesting. Okay. Just as there are heterocyclic analogs of benzene, there are also many heterocyclic analogs of naphthalene, quinoline, isoquinoline, indole, and purine. Oh, wow. Purine is tetrasubstituted. Quinoline, isoquinoline, and purine all contain pyridine-like nitrogens that are part of a double bond and contribute 1 electron to the pi. Indole contributes 2. Same with purine. But these other ones contribute 2. This contributes 2. Or no. These contribute 1. This contributes 2. This contributes 2. Among the many biological molecules that contain polycyclic aromatic rings, the amino acid tryptophan contains an indole ring, and the anti-malarial drug quinine contains a quinoline ring. Bro, look at that tryptophan. Tryptophan is used to make serotonin, by the way. That's why it's so interesting. In the body, your body literally synthesizes serotonin. And if we look at serotonin's structure, it has this aromatic indole ring. Wait, why are we getting the worst pictures, dude? I swear this SEO stuff. SEO is a cancer, man. It's trying to game the system. But here we go. So you can see here that there's going to be 2 electrons contributed to the pi system. We have 2, 4, 6, 8, 10. So we have this indole body. You know what's weird about neurotransmitters? It's not like ligand gated like ion channel. Like that was kind of my whole impression for my whole life, is that since I understood anything about neurons at all, I always just assumed that the big neurotransmitters, dopamine and serotonin, were just ligand gated channels. And that's not true. They're like G coupled protein receptors or ligands or something. See, actually, let's just open that back up. Anyways, it doesn't matter. It's too in the weeds for right now. All right. Adenine and guanine. Oh, wow. Oh, that's why you call them the purines. The pyrimidines and the purines. Huh. Interesting. Dude, I love these freaky bicyclic rings. I gotta get on that. Understanding the bicyclic rings. Azolene, a beautiful blue hydrocarbon, is an isomer of naphthalene. Is it aromatic? Draw a second resonance form to that shown. Um, yeah, I think it's aromatic. Yeah, this is the resonance structure that I just drew. How many electrons does each of the four Okay, so it's two or wait, one, 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 two. Wait, why did they draw this so weird? Two, one, one, one. Low key, I gotta skip this section. There's no way we can go over this. As much as I'd like to, it's definitely not covered, and wow, look at that thing. Okay, so actually, I think that 29, 33, 36. Maybe I should do these actually like right before the exam. I could look at them, but I kind of want to just get through chapter 16. 16 is going to be more like kind of what we're used to. Okay, so I'm gonna take a there you go to the bathroom, and then we'll get on chapter 16. Okay. Okay, actually, I'm gonna go eat dinner. Father's Day.